This is number 104 in chapter 15. 104 is basically talking about trying to determine the pH of a solution, but this pH, or the solution rather, involves a conjugate acid or conjugate base. And so I'm just going to do part A from 104, which consists of a 0.20 molar potassium formate solution. So Tro writes this as CHO2. Again, this is really indicating the potassium, indicating that there's a plus. There's also a minus side to this. I would tend to write this as indicating charge. This is really the salt of formic acid. So instead of having that acidic proton there, we have a potassium ion, so this is a salt. And so this means that this is not going to behave like an acid. It is a conjugate base. It's a conjugate base of the parent formic acid. And so as a result, we need to write an equilibrium expression, right? Remember, the potassium does not impact. This simply dissolves away, and it's really the anion, the formate, that is going to act as a conjugate base, deprotonating water to generate formic acid and hydroxide. So it acts as a base, and so that means we have a Kb, which would be equal to our products over our reactants. And so ultimately we need to figure out hydroxide concentration. Once we figure out hydroxide concentration, we can determine H3O plus concentration and then get at pH. If we look in our table, right, formic acid is a weak acid, we can look up the Ka for the parent, which is 1.8 times 10 to the negative fourth. Remember that when we're talking about a conjugate, we have to do a conversion. That the only thing that's going to be listed in the table is parents. Parent acid, parent base. And so we have to use this equation, Ka times Kb equals Kw, in order to rearrange and solve for the Kb of the conjugate. And so that means our Kb is going to be equal to 1 times 10 to the negative 14th over what we got from the table for the parent, 1.8 times 10 to the negative fourth, and that gives us a value of 5.55 times 10 to the negative 11. So that is our Kb that we're going to use over here. But now we need to generate an ice table in order to basically get at what X is. And so we would have our starting materials, our products, and our initial, our change, and our equilibrium. We have a concentration initially of our formates, none of our products. That tells us where our positive change is going to occur. And so those are our equilibrium concentrations. So now that we know that, we can use our Kb and plug it in above. So I'm going to erase some of this, make some more room. So kind of stepping off from here, our Kb was equal to that 5.55 5 times 10 to the negative 11th. And that's going to equal x squared in the numerator and 0.2 minus x in the denominator. Very small equilibrium constant. That means we're going to favor starting materials. So this change is going to be removed, since that change is going to be very, very, very small, since starting materials are so favored. And so now we have our reduced equilibrium equation, and now we can solve for our x. And so x squared is going to equal that 5.55 times 10 to the negative 11th times 0.2. I'm going to take the square root of both sides, and that gives us x, which is our hydroxide concentration, and that is equal to 3.33 times 10 to the negative 6. From that, we can get our POH, right? Our POH is equal to the negative log of our hydroxide, or that POH is equal to the negative log of 3.33 times 10 to the negative 6, which is equal to 5.47. So sorry for running off the board there. Let's kind of start again here. So we actually figured out what x is using our ICE table to be 3.33 times 10 to the negative 6, and then we actually determined our POH to be equal to 5.47. So if we make just a little bit more room, right, our POH, which we just solved for, was 5.47, right, and so we can get the pH, which is equal to 14 minus our POH, or our pH is actually equal to 8.53. Does that make sense? Yes, because we're starting with a conjugate base, so we should expect an alkaline pH or something greater than 7, which we do. And since we did make an assumption, we should check it. We started with 0.2 for a concentration of formate. Our 3.33 times 10 to the negative 6 was our change, and when we do that, we get 99% unchanged in that starting material, and so that means that we made a good assumption. And so our pH of 8.53 is correct. That is number 104, part A in chapter 15.